favorite game show, 15110 made us do it, where our player Amanda Hong has the opportunity to win big if she gets lucky. Today, we have a card that is worth $235,672.12. Is it behind door 1, door 2, or door 3? Alright, Amanda, which door will you choose?
I'll choose door 2.
Alright, we have heard Amanda's answer, but we want to help her out a little bit more. Will our lovely assistant please help us open door 1? Now, you are left with two choices, door number 2 and door number 3. Do you want to stick with door number 2, or do you want to switch to door number 3?
Since door 1 is not eliminated, most people assume that the other two doors will now have an equal 1/2 probability of bringing the one with the car, and therefore they see no added benefit to switching doors. However, this logic is flawed. In order to clearly explain this probability concept, we'll simulate the multi-hole problem using lists and the Monte Carlo method.
A list is a data structure that is useful for storing and accessing data. It is made up of elements enclosed in square brackets and separated by commas. A list can have no elements, one element, multiple elements that are made up of different structure types or of the same structure type. This could include booleans, strings, characters, numbers, etc., or even other lists. There are many interesting ways we can manipulate lists.
To create a list, just use brackets or use the function list. Similar to accessing a specific character in a string, you can access a specific element in the list by using an index. Index starts with 0 and not 1. Oftentimes, incorrect indexing can lead to an out-of-range error, which simply means that your list index is trying to call an element that does not exist. You can also slice lists in the same way that you slice strings. The beginning value is inclusive while the ending value is exclusive. There are both non-destructive and destructive ways to modify lists. First of all, you can combine or concatenate lists by using the plus sign. If you want to non-destructively modify the list, you can create a separate variable. But if you want a destructive method, you can use the append function, which simply attaches individual elements to your existing list. For sorting, list.sort is destructive, while b equals to sorted list is non-destructive. For removing elements, you can use either the remove function, which is destructive, or you can use the pop function, which returns an index value to you while not changing the list itself. Notice how lists preserve the order of the data. There are many other methods to working with lists. Some include finding the length of the list, which basically finds the number of elements in the list, and finding the maximum and minimum values in the list, and finding specific elements in the list using the in operator, and looping over lists using for loops and while loops, and creating copies and aliases of lists.
Another really cool thing about lists is that we can use them for Monte Carlo simulations. The Monte Carlo method simulates probability using repeated random sampling to solve problems that may actually be deterministic in nature. It is necessary to note that the higher the number of trials you run, the more accurate your estimate will be.
Bringing it back to the Monty-Hall problem, I need to determine whether I'm better off sticking to my first choice or switching, or is it just random unpredictable probability. So in this case, as you can see, there are 3 doors, so the probability of choosing correctly for the car will be 1/3. But then the probability of choosing incorrectly, because 2 goats are in 3 of the doors, it will be 2/3. This is a probability problem, and we can simulate it using the Monte Carlo method.
Now we will show you how our function choose_door will arbitrarily give us an element from the list. We got an N, another N, another N, and then a Y. Our second function, child succeeds, will return a Boolean value. It will return true if our function choose door generates a y. It will return false if choose door generates an n. Our third function, probability of choosing correctly, simulates us running this problem multiple times for multiple trials. We set successes as 0 for the start, and then we run a for loop which counts how many times or how many number of successes we get. Every success is counted when trial succeeds is equal to true. This means that our choose door function did generate out a y. And then we will return successes over trials because this is the probability of how many times we've chosen the correct door out of all our total number of trials. Now we will show you how this code works. If we run our function at 10 trials, it will give us 0.5 probability of us choosing the correct door without switching our answer. This is not accurate at all. We know that the actual probability should be 1/3, which should translate to a decimal number of 0.33. Let's try running with more trials. 100 and okay, that's closer. Even closer. Let's see if we can get a little bit more. Yeah, that is pretty close to the actual probability of 1/3. Now, we have solved the brain teaser of this problem. What is the probability that Amanda will win if she always switches doors? Let's think about all the possible outcomes of where Amanda will win. Remember, as a game show host, I already exposed one of the goats behind the door. Let's say it's this one. I showed this to Amanda. So if Amanda chooses the wrong door on her first attempt, sees the goat behind the second door, and decides to switch to the last and remaining door, she will always win. In other words, for Amanda to choose the right door after switching, she must first choose the wrong door and then, luckily, select the right door on her second attempt. Likewise, in order for her to choose the wrong door after switching, Amanda must first choose the right door and then unfortunately decide to switch to one of the other two doors. However, the probability of her winning is not the same for whether she decides to switch or not, because seeing that there are 2 goats out of 3 doors, we know that she has a 2/3 probability of selecting incorrectly on her first try, which means that if she decides to switch, she will have a 2/3 probability of winning. Using this logic for the other side of the argument, we know that she has a 1/3 chance of choosing incorrectly if she decides to switch, because that would require for her to choose the car and then incorrectly switch to another one. Therefore, this is debunked. It's not a random probability question. It is always in Amanda's favor to switch doors.
I'll switch to door 3.
Alright, let's open up door 3.